Okay, hello everybody, good morning. Welcome and thanks very much for joining this AFN Network Plus webinar on using artificial intelligence to reduce agricultural emissions, risks, opportunities, trade-offs and research gaps. So I'm Jess Fredenberg and I'll be your chair today. I'm based at the School of Environmental Sciences at the University of East Anglia, where I'm the Knowledge Exchange Fellow for the AFN Network Plus. If you don't know who AFN is, and this is your first time with us, we're a UKRI funded project focused on identifying research gaps that could help reduce emissions in the UK agri-food system in what is this critical decade. We've got, I think, around 2,500 members now across the UK. So if you've not joined, please do. I'll put links in the chat shortly. So also with me today is my colleague Vicky Triggle, who's based at the University of West of England. If anything happens, I go offline or anything, Vicky will take over. And our speakers today are Andrew French, Paddy Tarbuck, and James Strong, who I will introduce properly as we go along. So today's topic, artificial intelligence or AI is fast opening up a world of new possibilities in multiple areas and a lot of questions too along the way. So for food and farming, a big question is whether and how it can help us reduce emissions faster in what is a critical decade for tackling climate change. So alongside this, though, of course, it's also raising a lot of questions, a lot of issues for discussion, such as are there risks of using AI in agriculture? Might there be any unintended consequences, and what also might be the trade-offs? It also begs the question, what needs more information, resourcing, and research to ensure that we can make the most of AI and guard against any risks and negative outcomes. So I think today we might end up raising more questions than we answer, which I think is absolutely fine. AI is still very much an emerging technology; it's changing rapidly, and we're kind of trying to keep up with it. So I think let's go kind of into this webinar, I think, with a sense of inquiry, and not worry if we don't end up answering all the questions. But I think it's really important to be raising all these questions at the moment. So what we're going to do today is, like I said, we've got three speakers. So Andrew is going to kick us off in a minute, looking at more general kind of questions around risks and opportunities of using AI, and particularly with crops. And he's going to give us a really good sort of introduction to AI, get us all up to the same understanding. Then James is going to come in and offer us a case study, so a project that he's been working on using AI and machine learning related to miscanthus as a biocrop. And then Paddy will come in and again look at risks and opportunities, research gaps, but looking more at livestock and net zero. So I think Andrew, if you want to get your slides ready, so we'll have a 30-minute Q&A afterwards. So if you've got questions as we go along, please put them in the Q&A box so I can find them easily, and save the chat box for any discussion you want to have or sharing of links and things like that. I will share some links in a minute. But Andrew, yes, you're good, your slides are all ready. So I will hand over to you in just a second. Let me introduce you properly. So Andrew French is a professor of computer science at the University of Nottingham, where he leads the computer vision lab. He has worked closely with plant scientists on a wide range of image-based data analysis challenges for nearly 20 years. This means today developing an array of AI-based approaches to image analysis of plants and crops. Andrew also leads the AI and Biosciences Community Building Network, along with a team of co-leads from around the UK. So Andrew, I will hand over to you.
Okay, great. Thanks very much, Jez. Morning, everyone. Really pleased to be here. Thanks for the invite. Thanks to AFN for inviting us. So, as Jez said, I'm a computer scientist, so I'm not a kind of core livestock or crop person. I'm a developer of computer vision techniques, really. So, I've been doing that for about 20 years or so. And for most of that, we've been working with plants and crops in different forms. So definitely have some knowledge of the kind of crop possibilities of AI. And what I wanted to do today was really just to provide a pretty general introduction, as Jez said, just to kind of set everything else in context and get you thinking about some potential applications and some things that we need to think about when we're working with AI. So I thought I'd start with the kind of the easy in quotes question, but actually it turns out it's quite hard. So it's relevant actually. So in the news this week, I was reading that Amazon have released the top questions people ask Alexa in 2024, and this was up there. So people don't know what AI is, what it means, and in general what it means when we're talking about artificial intelligence. So I just got a slide here really just to kind of set that in context. I would say AI is a pretty subjective term. So people have got different ideas about what it means. When you work in different areas, you use it in different ways. And I think my interpretation of it is definitely coming from a computer science background, and it's also pretty broad. So I'd say it's pretty, a broad definition. So for me, when we're talking about AI, we mean learning from data. So that's not actually every single AI technique, but these days, most of the ones that you read about, most of the kind of cutting edge ones that people are using, is a form of what we call machine learning, which means that rather than kind of very prescriptively writing lines of code to do very specific tasks, instead we provide a framework that allows a computer, an algorithm to learn from data. What it's learning from that data is pattern recognition. So what AI is really good at is looking for potentially quite complex patterns in data. So seeing things that perhaps we can't see as humans in really, really large data sets. And it does this via a series of different kind of algorithms and approaches. So as I said, AI is an umbrella term, and there are loads of different models or algorithms, tools, if you like, for getting this information out of data. So these different kinds of sort of pattern recognition approaches. So there isn't one tool in the toolbox, if you like. There's a whole collection of different computational approaches that we can use that all fall under the umbrella term of AI. So it's very broad, covers a variety of techniques and models. And some of these come from statistics, machine learning, computer science, and maths. But they're all to do with working with data and turning that data into much more meaningful and useful information. A lot of AI that we talk about today, those tools are things like deep convolutional networks, CNNs, large language models. So CNNs are, I'll show you a quick example in a minute, but a way of looking at, in particular, image data. So I developing techniques that work with images, but you can apply AI across all kinds of different data sets. So numerical data, text data, image data. Data to a computer is data, right? But there are different ways of thinking about it. So images in particular have got certain properties that perhaps a list of numbers don't have. So some of these approaches are really good at working with images, and deep convolutional networks is one example of an algorithm that will do that. If we're talking about text, obviously we've got large language models, things like ChatGPT, which are really kind of recent, just come out in the last couple of years, really into the sort of public domain. Large language models are a form of what we call generative AI. Generative meaning it generates something, so text in the form of ChatGPT, but you can get image generation approaches as well. But that's not to say that's all there is. There's a host of other techniques and other kinds of models that are coming along, quite rapidly, and allowing us to analyze data in different ways. And all of these approaches build on probably 50 years of development, different kinds of development in computing and maths and those kind of backgrounds. But I think what's changed recently and what's really allowed AI to become mainstream, if you like, is a couple of things. One is kind of software related. So we've got better programs that we can use to develop AI. And the second one is compute. So we've got a lot more computer power now, which is what a lot of these models will use. I talk about pattern recognition and interpreting things in data. And so one kind of really general way that a lot of these models work is they turn the raw kind of numbers or pixel values in images into more useful intermediate information. So here we've got an image of a leaf and we're turning it into kind of highlighting the edges. So we're kind of highlighting using an algorithm where the edges around the leaf are. Now, any kind of AI system will do things like this. It will turn an image into more useful features, right? And this is kind of what our eyes do as well, right? And our brain, we pick out information like boundaries around objects and patches of texture and things like that. So a lot of these AI approaches will again look for these patterns that represent higher level details about the image, edges, lines, and even all the way up to kind of concepts and things like that. And this allows us to solve pretty complicated problems. So here's an example of a wheat data set, which is available online. And we're trying to here categorize or locate where the wheat heads are in the image. You can see it's quite a challenging thing to do. I think one of the dramatic things about AI is, even 5, certainly 10 years ago, identifying where the heads of wheat were in an image like that is really, really hard. You've got a lot of complexity in these kind of agricultural images. You've got challenging lighting, shadows, you've got things like weeds in the background, stuff like that. It's really, really hard to do it. What AI allows us to do is to do this really sort of complicated insight into these really, really challenging data sets. And that works for images, but also, as I say, numerical and other kinds of data as well. So what AI is giving us, whatever the tool is, the idea is it's giving us more insight into really large data sets. So how does this work in practice? Just to overview kind of how it would work if you were developing AI techniques. As I say, you have to build on data sets. So we have to collect a lot of data and label it, often by hand still. So in order to train these algorithms, we need annotations and labels collected by experts, perhaps via bespoke software tools, so that the computer knows what it's looking for in the images. In this case, again, ears of wheat. There's normally some coding involved. So we need to develop algorithms which are going to build these models or networks, as they're sometimes called, that are actually going to do the work of doing the pattern recognition, doing the extracting of features from images and things like that. And once we've done some coding, we need to train the models. So that means that the models need to look at all the data that you've captured. So looking at all the images that have been labeled and trying to learn what it means to kind of mark out regions of these images or detect certain bits of the image. So that training process can take a long time. It's quite compute intensive. It's the GPUs here. So these days, we have a lot of dedicated hardware that allows us to do that. It's the training which is the most computationally intensive part of AI. Of course, once you've got a network, you need to test it. You can't just assume it's working. So we test them on dedicated test data sets that haven't been seen during this training process, so we can evaluate how well it would work in the real world. And often then we want to build these algorithms into a tool that we can then deploy for people to use. So some common tasks in AI, don't worry too much about what's going on in the middle here, but if you are interested, this is an example of a convolutional neural network. So it's taking an image, and as you can see, we're kind of going up in scales here. So we're going from pixels into kind of higher level details. So the idea of these networks is they go from pixel information where we've got quite raw and noisy color information in an image, along to, in this case, a classification problem. In classification problems, we're applying a label to an image. Is it a leaf? Is it an ear? Is it something else? So we're teaching an algorithm to apply a text label. Other kind of tasks that AI can do is kind of mapping out regions of images. So again, here we're still with the wheat ear example, but actually we could be marking out regions of disease or something like that. And when you've got a region, you can measure things about the region. So you could measure the area or the width or the length or things like that. Um, you can do much more fine-grained analysis as well. So perhaps more of interest to kind of breeders and growers or research projects is you can get really detailed categorization of, in this case, a root system. And so we're able to get out a lot of measures here about the length of all the different routes, the angles of emergence and things like that. Again, all via an AI algorithm. And these things work really well. So, another task you might want to do is to kind of pinpoint things on an image via a heat map, so marking particular regions. And in this case, we've trained a system to mark the sort of the tip of the wheat here. And actually, what the AI said was, well, actually, I think there's two tips of ears here. There's one there and there's one there. And actually, if you look really closely at the image, there's actually kind of two ears on top of each other. And again, 10 years ago, that would be a really, really challenging problem for us to solve. But here we've got AI systems that are able to look for those patterns in the data and really do quite impressive things like that. So you could use a system like this, for example, to identify, again, maybe disease or pests or any kind of feature that you want to train it to recognize. So a few things to think about, some perhaps opportunities around AI in agriculture and crops in particular, perhaps. We've seen through these simple examples how you can get quite a lot of insight into really complicated to interpret images and data. One thing that AI will allow us to do, as will many other kind of algorithms that you can develop in computer science, but perhaps the end goal is automation. So perhaps using robotics to capture data or sensors mounted on UAVs or tractors or whatever it is that we're doing, we can collect a lot of image data or other sensor data. The challenge is then analyzing it. And a lot of these AI systems, because they can work so well at detecting these really complicated patterns, we can automate some of that process. And that gives us a way to monitor in a detailed way things like fields or glass houses. I think another really big opportunity of AI is just how fast it's developing. So, every year there's more and more advances, more things that we can try and use to try and build more efficient research systems and software apps that can help us. Obviously, it comes with some challenges, like as with any kind of new technology. There's an understanding and training barrier. So not just in terms of developing it, you really need to be a coder. But even using the tools, you need to understand where they can be used, where they can't, where one model might be suitable versus another model. So there's definitely a training element to this and a kind of feeling that we need to understand as a community what AI is and what it can do for us and what it can't. I've mentioned data. We need a lot of data. We need a lot of labeled data to make these things work. And that obviously comes as a kind of a barrier, collecting these data sets, especially in quite specialized areas. You might not be able to find any images for one particular kind of crop in a particular situation. So if you want to build a system, you might have to collect your own data to do that. And how well a model that you've built will work on another field, another farm, another data set is an open question and something that we need to test when we're developing this software. Some of the algorithmic approaches are getting better at being generalizable. There's certain tricks we can use to help generalize data sets into other domains, but we want to build models that work across the biggest set of data that we can. Equality of access to AI. So that means both, everything I've talked about, really the training, the understanding, but also compute. So I said it takes quite a lot of compute to train these things. And certainly some of the really, really big, especially generative AI models that are coming out, not even within the realm of universities to train these things, right? So some of the really big models, the data sets are just so big and the models so powerful. It's really kind of down to real specialists like industry to train models, and then we can kind of adapt them and reuse them in different ways. Just to finish up in 1 minute, so in this kind of context, as Jez mentioned, I'm also part of the AI in Biosciences Network. And part of our aim is to try and help with some of these things. So to get us thinking about training, raising awareness in events, thinking about how we can use AI in different situations, of which crops, livestock, and agriculture is definitely some areas that we're interested in, although we're much broader than that and kind of go across the whole remit of BBSRC. So we've been going for about a year, and we've got a team of co-Is from around the UK, and we're kind of just putting together events, talking to other networks at the moment, trying to do things like this and raise awareness of AI and get people more involved in the community when they might not have otherwise been. So I'm probably out of time, so I'll leave it there. I'm more than happy to answer any other questions about AI in biosciences or AI at the end. So with that, I think I'll wrap up and I'll pass over to James.
Thanks, Andrew. That was really good and a really good, yeah, just a great kind of general introduction. So thank you. Okay, we will move on to James. James, if you want to get your slides ready while I introduce you. Oh, so James is a research software engineer at Aberystwyth University, currently working on the Miscanthus AI Net Zero project, where his role involves investigating how AI models can support plant breeders in selecting and breeding processes. His research background lies in bio-inspired AI, exploring how biological systems can inspire innovative approaches to navigation and problem solving. So James, over to you.
Cheers. Thank you very much. Yeah, so I wanted to speak to you today about the project that we're working on, which is a joint project in Aberystwyth, Lincoln, and Southampton universities. It's funded by the EPSRC, and we're looking basically at how we can improve biofield features in Miscanthus. Our work stream is specifically looking at how AI can help with that. And today I was just going to speak to you about our implementation as a kind of case study to show how AI can help. So what I'm going to do today is I'm going to speak to you about our specific aims, give you some background and context so you can appreciate what it is we're trying to do and how we're trying to achieve it. Spend a little bit of time on some light implementation of how we've gone about it, and then speak to you about the success and the problems that we've had with our results. So our very specific research aim is basically looking at how AI can improve the predictive modeling and use that to accelerate the Miscanthus breeding cycle. So historically, when breeders are looking at crops, they're going to make crosses, they're going to take measurements, and they're going to update their models. And what we're hoping is that AI can step in and look at using and leveraging genotypic and phenotypic data to speed up this process. Our particular work stream is looking at combining SNPs and nurse data using random forests for feature selection and modeling. And we're able, or hopefully able, to predict yield, but also other elements like cellulose and lignin.
James, sorry
yeah,
to
sorry.
interrupt, but we can't see your slides.
Oh.
It says that you're.
I could see them.
I could see them, yeah.
Can you? Okay. Can everyone just in the chat please just let me know? Can you see them? Okay, lots of people saying.
Cool.
Can anyone not see them? No. Okay, everyone seems to be able to see them. So carry on. It's just me.
I think there's a few no's in there, Jez.
Okay.
I can't see them now, actually.
Yeah, I've stopped sharing to see if I can fix it.
If you can reshare.
Yeah, so yeah.
Some people couldn't.
Okay, can you see them now?
I think it's just loading. Yes, I can see them again now. Okay,
Okay.
can everyone see? Everyone put on the chat.
Sorry about that.
Yeah, everyone can see. Okay, carry on. Yeah, thank you.
Okay, sorry. Yeah, so so our particular work stream is considering two things. Can we make better predictions by combining phenotypic and genomic data? And then also, do random forests outperform the existing techniques that have been applied to this data set? So just so that you are aware of what it is that we're working on a data set that's called the 2TT data set. It was 136 genomes that were planted and collected at Aberystwyth University. And the reason that we're interested in Miscanthus is because it has a large biomass. It's got robust growth, so it'll grow in maybe not ideal soil conditions for other plants. And it's a C4 grass, so it strips carbon out of the atmosphere. And then I'll quickly go through the two different datas that we're dealing with. So we've got NERSC data, which is near infrared spectroscopy data. And what we're basically doing is we're using near infrared light to quantify the composition of plant material. So we have an example of kind of 5 genomes, the data you'd get out of them using NERSC. And it's basically kind of like a waveform. And we're really interested in NERSC because it's non-destructive, so we don't have to pull plants out of the grounds to get those readings. And it's relatively cheap and easy to collect, comparing it to other genotypic kind of datas. So we're currently looking at attaching NERSC cameras to drones that can kind of fly over fields and get the collection of data that we need. And then quickly, just to cover off the genomic data, what we're basically looking at is variations at single positions along the DNA sequence. So this is a tiny little example of the data set. The whole data set is 50,000 features. And basically, these markers are used to identify the differences genetically between each plant. So we combine these two datas, and the genomic data is the more classical way of looking at these problems. So I did mention previous results, and people have already looked at this data set, and they used ridge regression to see if they can predict dry matter, which is our yield, cellulose and lignin levels. And you can see there that we've got quite a improved accuracy and prediction using the NERSC data. And so you might be thinking, if the NERSC is so good at predicting, why we want to combine. And the reason we want to combine is because we know that the genomic data is heritable and the NERSC data is environmentally impacted by local features where it's grown. So we want to try and leverage those two predictive abilities and ensure that we're not just getting good at that we're predicting heritable traits in plants, basically. So the implementation we've been using is random forest. The project was interested in using random forest because they have a degree of human readability, which I don't want to get into a massive debate about right now, but they have this element of human readability. And they've been shown to previously be successful when dealing with noisy and biological data. But really simply, the way that this random forest is working is we create a decision tree based on the information we have about the objects that we're trying to classify. And we make hundreds of these small trees on subsets of the data. And then we combine them into what we're naming a random forest. And we take the selection of decisions that each tree makes and come up with a kind of final decision on a particular object. So it gives us a kind of a complex way of classifying, and the classification is the more standard approach. We're actually using random forest for regression here, but the same kind of approach applies. So the reason we're using something like this is because the data sets are quite challenging. The samples are quite highly correlated. The target variable distribution is problematic in the sense that we have very few examples from the lower range and the higher ranges of yield for this example. And we have a large number of features, but with a small number of samples. So the NERSC data has over 1,000 features. The SNPs, we're talking 50,000 features. And we end up with a problem that you might have, or a definition for this problem that you might have heard before, which is big P, little n. So we have a lot of predictors and not a huge amount of things to predict, which can be really problematic for AI and machine learning. So the normal approach here would be to try and reduce the dimensionality, to remove the number of features or squash the number of features. And those kind of typical approaches weren't successful with this data set. So what we decided to do was use a method called iterative feature reduction. So we use the way that the random forest creates its feature importance to rank the overall features of the data set and start to iteratively remove features that weren't contributing to predictive results. And we would expect to see the predictive ability increase until the performance plateaus, and then we're relatively confident that we've reduced features down to ones that are important for the targets that we're trying to predict. And this was relatively successful for our nurse data. We saw a higher prediction accuracy than that was previously achieved in the ridge regression. But one of the challenges, or one of the problems with using this kind of technique, is that you can lead to a problem called overfitting, where what we're doing is we're not very generalizable to new data. We have a small amount of data points that we're trying to prove, and we've overfitted, and we're very good at predicting those, but not very good at predicting new ones. So we did some permutation testing, and we held back some data to verify that these results were legitimate. And although we saw a slight decrease for new unseen data, overall the results still held. However, when we moved this process across to the SNP data, we found that the same processes just didn't hold up. The additional data size based on the input features meant that we were able to achieve an over sorry, excuse me. We weren't able to achieve the same level of prediction that we would have been able to achieve with a nurse, and that we were overfitting to data that is meaning that our results aren't legitimate. So we saw that the two techniques worked really well with one data set and wasn't applicable for another data set. So one of the conclusions that I'd like you to take from this is that we need to be really careful with how we deploy, report, and test our AI models. So yeah, that is the conclusions for those talks. Apologies if you couldn't see my slides. I'm hoping that that wasn't too much of a big problem. But yeah, thank you very much.
Brilliant. Thank you, James. Paddy, if you want to get your slides ready, that would be great. So Paddy Tarbuck is Innovation Lead in Agri-Food Sustainability at UK Agri Tech Centre, where he drives sustainability towards net zero and biodiversity goals through collaboration across academia, industry and the third sector. His career spans civil society, finance, trade associations and the UN. And Paddy's expertise includes carbon and nature markets, regenerative farming, and climate finance. So yes, James, thank you so much for that. Sorry, we're whizzing on so quickly, but that was a really good sort of insight into the sort of applied AI. So Paddy, if I hand over to you now, and yeah, we'll be looking into.
Can everybody see my slides?
I can see them.
Perfect. Great, and thanks for that intro there. Yeah, I think that probably, I'm pleased I'm up last here because it's been really interesting to see James and Andrew's sort of real world applications of AI, particularly sort of miscanthus there. So don't expect that from my presentation. I'm certainly not an AI expert. I'm coming at this from more of a kind of livestock and net zero perspective, as Jez mentioned, more of a interdisciplinary sustainability professional. So real kind of climate and social science, looking at the social costs of implementation of tech here. So yeah, I'm Paddy Tarbuck, Innovation Lead for Sustainability here at the UK Agri Tech Centre. Some of you might be familiar, oops, sorry, the slides aren't moving on there. Some of you might be familiar with the UK Agri Tech Centre, at least some of our legacy centres. We recently merged earlier in the year to form the largest agri-tech organisation in the UK, really trying to sort of drive stronger cross-sector collaboration and creating a sort of larger ecosystem where we work at that intersection between academia, industry and government. So we're really trying to sort of bridge the gap and drive innovation and adoption throughout the agri-tech sector. We've got a range of capabilities across the UK, ranging from respiratory chambers for measuring methane emissions all the way through to some of our stock bridge and vertical farming facilities. So we can connect you with those capabilities as well. So AI and net zero, some of the risks and opportunities. So quick sort of framing, I guess, of the problem, and we're probably all very familiar with the impact and the well-established impact of the livestock sector on environmental impacts. It contributes 10% of total greenhouse gas emissions in the UK, of which 71% of nitrous oxide emissions and 49% of all methane emissions. Within that, ruminants through enteric fermentation represent over half of UK methane emissions, so pretty sizable. And we've had reports, such as FAO's livestock long shadow, looking at the impact beyond that. But now we're kind of shifting the narrative a little bit from this long shadow to how livestock, particularly grazing animals, can be used in the right farming systems to maximise resource use, circularity and carbon sequestration. And we've seen that with farmers as well, where 62% of farmers in the recent government study consider greenhouse gas emissions important for farm business decisions. So it's really kind of empowering to see that. And the emissions intensities from the livestock sector on the whole have decreased. And we've done that largely through efficiencies, innovation, circularity, manure management, precision farming, all kind of great tools, but not moving the dial fast enough. So we really need to accelerate that. And we're seeing this through some of the recent studies coming out looking at the role of large animals in climate change mitigation, the potential soil carbon sequestration potential of that. And just a note here that 70% of land in the UK is farmland, and there is further potential there for reductions and removals, and we need the right enabling technologies to support that. One of those enabling technologies is AI. And I should start by saying, when you mention AI to a livestock farmer or a livestock sector, it's probably further down the pecking order than artificial insemination and avian influenza. So worth mentioning that we are talking about artificial intelligence when we speak to livestock farmers. And Andrew's covered this off pretty well, but effectively we're talking about large data systems and processing of those data systems to make predictions, improve efficiency, productivity, and sustainability in the sector. And it's really that machine learning component that I'm probably going to focus a little bit more on here. But some of those large language models and our kind of advanced AI tools, really summarizing all of the wealth of data on farm and packaging that to understand trends and patterns and provide insights direct to farmers throughout the supply chain as well. So a really useful tool, and we're still figuring out ways to do that. There is a real kind of data overload. I guess the bigger picture here is that there is a data overload at the farm level, and it's a burden for farmers. So we need to recognise that, and we need to have the right support and tools to support advisors, farmers, and everyone throughout the supply chain, so we can simplify this through AI. The application of AI in farming is pretty well applied. We saw the presentation just then from James, but it is already in practice to manage a livestock health. And it's one of the kind of indirect or direct forms of climate action that we can see. And we're involved in a project just to highlight this with hoof count. It's quite simple, I guess. An image is taken, photos taken of a hoof. The AI imaging tool detects anomalies. So in this case, a lesion. And the large language model will support that by explaining possible causes for lesions, suggesting interventions, and connecting farmers to a vet, for instance. In terms of the opportunities and the risks, the really kind of big picture, all solutions are here to kind of support farmers and empower data-driven decision making. So we don't want to take that away from farmers. We want to support them through sort of evidence-based solutions. One of those, I guess, is soil and water management. So monitoring soil and water usage, helping farmers reduce resource consumption, increase efficiency, reduce runoff risks, and decrease emissions. So you've got the example potentially of irrigation systems in a crop system, how that can be used and utilized by AI. Precision farming, I guess, is the one that most people kind of will go to, is how do we process complex amounts of data to be able to deliver the right insights and optimize precision farming at the farm level. Feed efficiency is quite an interesting one, I guess, is maybe looking at, and not to displace any nutritionists here, apologies on the call, but looking at kind of automated feeders. So you can analyze each animal's nutritional needs, so you can work alongside feed troughs and some of the automated feeding systems there to potentially dispense customized feed portions. And that's obviously, particularly for the monogastric sector, a massive proportion of their carbon footprint. So, real kind of opportunity there as well. Animal health and welfare is probably one of the most readily applied in the livestock sector in terms of AI, but looking at monitoring health, movement patterns, feeding behavior, temperature and productivity in real time. And as we saw, early detection of diseases or stress or heat stress, for instance, which empower and enable preventative actions. So I'm aware of, I think, a project with poultry farms looking at indicator or detecting sound and using sound to indicate poor welfare in broiler systems. Breeding, mentioned earlier in terms of the crop point of view, but identifying genetic traits and better feed to product ratios, so contribute to the long-term sustainability there. Carbon footprinting, particularly interesting, I guess, and we've covered this in previous AFN webinars, but looking at collectivizing and harmonizing some of those methodologies and how we can build in some of the accurate emissions tracking at the farm level rather than some of the maybe higher IPCC level global figures to represent data in different format. And then, of course, policy design and support, evidence-based regulations and incentives. So we can look at how SFI payments, for instance, are empowering farmers to create sort of sustainable farm systems. But within that, I guess we also have some of the risks, some of which have been highlighted already, but data sharing, ownership, safeguarding the ownership and value of that data. We need to make sure that's safeguarded. I think the one perhaps to focus on here is the energy costs when we talk about net zero. There is, of course, a huge amount of data running through some of these systems and the processing systems, and that creates a huge energy demand. We're already outstripping that energy demand. So there's I guess a wider ethical question of, is this sustainable as a solution, and matching AI with the right solutions rather than sort of looking at it as a silver bullet solution here. We don't want to sort of create more work and more energy demand where we don't need to. Job security, in particular for the rural communities that represent the majority of the farming sector and the agriculture sector, is what's the impact and the job loss and the job displacement potentially from AI and doing some of those farm-based tasks. Education and training. So I think the crucial thing with AI is, yes, it's a complex data processing system and all the different tools we have available there, but we are still reliant on human interventions and training to develop those models, as well as ensure effective data collection and monitoring. So there's leading on to the data bias piece, that it's only as good as the data fed into them. The data is biased or incomplete, that the AI is not as accurate. So we need to keep that sort of in mind as well. And then the ethical considerations, which I'll probably lead to Q&A a little bit, but there are, for instance, what if AI provides insights that prioritize efficiency over animal welfare? This is a kind of key question, and where do we place ourselves and position ourselves when that is presented? In terms of the research gaps, spoke about it there, but the limited availability of high quality data, and in particular here, livestock emissions data by breed, by feed. There is more evidence and practice needed, and that's none more true than I guess the recent sort of Bovaer announcement and the backlash to that. There is also, I guess, the economic viability and scalability, which limits adoption for all farms. We want to represent and try and drive adoption on smallholder farms as well as some of the larger farms. They might not have the risk capital available to be able to get this on farm. There's also inconsistencies and gaps in quantifying and verifying long-term impact of AI interventions on greenhouse gas reductions. And of course, from being remiss of me to not mention the integration of local knowledge and diverse data streams into models. So, for instance, for biodiversity, how do we look at bioacoustics alongside remote sensing, and how do we integrate that with what the farmer sees in terms of that local knowledge and that real kind of cultural knowledge. There's also a requirement for us to work cross-sector here. So whilst AI might be a little bit less down the line in terms of application in the agriculture sector, we might see sort of huge amount in the financial sector. So there's opportunities to cross-sector collaborate there. And it was mentioned before in terms of building the models and the computer science expertise related to that. But the models that we build, are subjective in a number of ways. So we need to make sure we're upskilling sustainability professionals and upskilling social scientists to make sure that that data is represented and that worldview is represented within some of those models. You see it quite a lot in terms of how some of those models are presented in a quite black and white format, perhaps without a view of how the social components are built in. And then beyond net zero is how can AI support maybe some of the biodiversity and nature targets, and we're seeing that quite readily as well. Just a quick plug, I guess, on the UK Agritech Centre, we do support that innovation. We can support through funding support, bid writing, project delivery, and we do have a commercial farm network as well, where we're utilising some of the AI and machine learning components within that. So yeah, I'll finish there and stop for any questions.
Thanks, Paddy. That was really good, and you raised loads of questions there that I'm hoping we can now dig into. Before we get on to that, I'm conscious that we've only got 10 minutes now for questions. Paddy, Andrew and James, are you at all available to stay on an extra sort of 10 minutes or so beyond? Are you available for that?
Yeah, I can see that.
Yeah, brilliant. Okay, great. So we've got a few questions coming in, or a good few ones. I think this is quite a good general one from Lauren Leake-Smith, who was one of our speakers a few weeks ago, actually, from the Behavioural Insights team. Please, could you elaborate on the opportunity to use AI to optimise SFI? Is that, Paddy? That's probably one for you, isn't it?
Sorry, Jez, I was also looking at the question in the chat. Could you repeat the question?
Sorry, okay. Yes, the question is, please could you elaborate on the opportunity to use AI to optimize SFI? So I think this goes back to your point about using it for policy making, and how can policymakers kind of use it in that way?
Yeah, I guess it's a high level, and please, James, Andrew, come in a little bit more, but in a way, you've got you're punching data in, so you're looking at perhaps some of the attributional data. What are the farm practices that are being incentivized through SFIs? Take, for instance, the cover crop, and then monitoring what that means for biodiversity, what that means for carbon, what that means for all these different things. If you ask us to try and collectivize those all of those different data points, it's very difficult. But whereas if we build a model around that and plug it through a machine learning system, then perhaps there's an opportunity for us to get a quicker answer and a more standardized, effective answer on how SFI is additional to some of these ecosystem service outcomes. So I don't know if that sort of covers the question.
Andrew and James, did you want to come in on that at all? Was there anything you wanted to add?
I don't think I've got anything specific to add, James.
No, sorry.
No, that's fine. Okay, we got another question from Susanna Bolton, which again is a good general one to get us kind of started off. She says, at the recent Agri-Tech e-conference, Dr. Elliot Grant identified farm business model optimization as a key opportunity for the use of AI in the future. What is your view on this? So I guess this goes back to the point of, how can farmers make the most of AI in their businesses without feeling overloaded? It goes back to your point, Paddy. How can it be used in a way to optimize farming rather than just sort of add like another thing that they've got to do. Andrew, is that one for you, or maybe this is?
Perhaps I can kick us off. So I don't actually know details about what the farm business model is, but I can talk a bit about in general about how AI can be used in optimizing things. So I think it's a method by which you might be able to learn what parameters of a model can be used to improve like outputs or efficiencies or things like that, just as any other kind of computational tool can be. So the way I guess, see it used in the future is I would think it would be built into existing systems, existing workflows, much like we're getting AI built into things at the moment to help us do tasks. I think that will happen more and more, either kind of overtly or behind the scenes, whatever systems are used to try and help optimize or plan efficiencies and things like that. We could use these as a tool to try and do that. But I'm aware I'm talking very, very generally, so I don't know whether Paddy has anything to add, for example.
Yeah, no, Andrew, I think you've covered it well. I'm also not as familiar with the business model optimization, the farm business model optimization tool, but I guess yeah, you've covered it quite well in terms of the farmer perspective there.
Yeah, no worries. So hang on, I'm just dealing with someone on the chat. Yes, I know, Pat, you can't see the questions in the Q&A box. Don't worry, it doesn't matter if you're repeating them. It's just that I can't see your questions properly. If they're in the chat, they'll get lost. So please put them in the Q&A box. So this might be one for you, James, in the Q&A. This is a more sort of tech one.
Yeah.
From Ramin, who says, considering Google's recent developments in quantum computing, could you elaborate on the potential synergies between quantum computing and AI? How might these technologies complement each other in practical applications? Do you know, a very basic question for me, do you know what quantum computing is to start with? And if so,
Yeah.
can you
So
explain?
I am absolutely not an expert on quantum computing, so I am not at all qualified to comment on quantum computing. But in theory, the advances that we'd see in quantum computing is just going to give us more compute power. So the
what is quantum computing to start with? What is it?
Okay, so if you're looking at how we compute now, we are basically making decisions in zeros and ones. So we're able to say if something is on or off, and quantum computing, very simply, well, overly simplified, is giving us more options than that. So it means that we can compute things at a higher rate. It's probably slightly outside of the context for this webinar, but the upshot of quantum computing for AI would be that you have more compute power, and that is something that the AI is very reliant on. All of these machine learning models, kind of at their root, are seeing a lot of success at the moment because of the increase in compute power. So things that were theorized 15, 20 years ago are now very doable because of the increase in that. So I think it's maybe not hugely helpful for this webinar, but yeah, we would expect to see with the increase or a successful quantum computing would give us a huge extra amount of resource for AI. But I can't really say much more than that on it, to be honest.
James, I think you answered it very well. I'm also not an expert, but I would say that I think the advances that have been made are very theoretical, from my understanding. So we're definitely not at the point where there's going to be a quantum computing like immediately on the horizon, right? So it's a tool to think about for the future. And like James said, it has the potential to just add vast amounts of compute. We can do a lot more calculations, but yeah, definitely not there yet.
Okay, thank you. So question from Pat Haslop Harrison. She says she's very interested to note, so I think this was, I can't remember who said this, but someone said there's a limited availability high quality data, for example, on livestock emissions data. Maybe this was you,
I think it
Paddy.
might be me, yes.
Yeah, and she says, why is this, and how can funding bodies, journals, academics, etc., be encouraged to require publication of full data for publicity funded work, or what better methods might be used at field or farm level? So I think it's more of a general question, really, for what can the research community do to sort of increase that availability of data that is freely available as well.
Yeah, and I guess there's a few steps to that approach and that process as well. But what I mentioned, I guess, by limited availability of high quality data is you often see, particularly sort of livestock sector and livestock types presented in a certain way. So we've got a range of emission factors for beef. You might see on our world in data it presented in one format, maybe the higher range or the lower range or the medium range. What we do know, particularly in the UK, is perhaps that might be a little bit lower. Similarly, for there's a study recently that came out on slurry storage, where we potentially are looking at a 5-fold increase on what we have in our inventory, which means we're effectively under-reporting the emissions associated with slurry. So there's a requirement for the research community to be able to create sort of high quality data. And where I think the gap potentially is communicating that high quality data down through to proxies and measurements. So there's a real, I guess, burden on the carbon footprinting community and the carbon calculators to try and include that in recent versions, and for policy and regulations to ensure that we're updating inventory in the right kind of formats. So yeah, I guess a few different ways.
Yeah, thank you. So question here I want to kind of tie with a few different things around sort of ethics and access, from someone called Evie. He says, Andrew mentioned equality of access to AI as one of the challenges. Please can you elaborate a bit more on this? So I think this is a more general question, yes, about equality of access to AI, and also what that might mean in terms of training and skills, but also what it might mean in terms of how do we stop AI becoming something for the preserve of the big agribusiness. What does this mean for sort of small farmers and that sort of equality and power balance within the food system? Andrew, do you want to pick that one up?
Yeah, well, I can kick off, and then perhaps the others can join in if they want to. It's a big question,
Yeah.
especially if you're bringing in the kind of ethics as well as the equality. So I think, yeah, it's important to recognise that not everyone has the same access to AI tools, either developing them or using them, and there's a variety of reasons for that. You just might not have access to the data that you require to build some of these models, and as I said, some of the real cutting edge models that are out there are so big that unless you have access to billions of images, it's kind of that scale, you're not going to be able to build them. So, luckily, I suppose we're at a position where we can reuse models in different ways and kind of fine tune them into different domains. But there's definitely an availability of data, and even on a much smaller scale, you might not be set up to be able to collect, annotate, and train your own AI models. So that kind of speaks to the training and expertise bit as well. I think thinking about compute is important. And then I know there was a question about compute and, I guess, environmental impact of compute as well, and the balance of that with emissions. And that's, yeah, totally fair. Normally, most of the compute in AI is when you're training the models. So you can kind of train it once, and then once you release it and deploy it to smartphones or whatever it is you're doing, those kind of user models are much more lightweight, right? That's why we can run AI on our phone without having to have it connected to a big GPU system, right? Because they're lighter weight, which means there's less compute, it's using less electricity. So access to compute is probably more of an issue for being able to build and train your own models rather than using them in practice. And there's definitely been a kind of a line of research around what we call lightweight or mobile models, which are specifically built to do kind of smaller, easier tasks and run really, really quickly on quite low compute. So that's kind of, I think, from my perspective, the kind of equality of access is, do people have access to expertise, to the data, and to the compute needed to build it. And if you can't build your own, what access do you have to other systems? In computer science, and talking about sharing data as well, we're kind of used to publishing and sharing models and sharing data. But I guess, there's no, if you're developing something commercially, you might not want to do that. So there's kind of an academic route and there's a sort of industrial route to developing these things. Yeah, I've forgotten what the second part of the question was, to do with ethics, was it, Jez?
Yeah, it's more around how but I think you've really answered it. It was more around, how do you sort of stop AI becoming the preserve of big agribusiness, and agribusiness getting ahead and leaving smaller family farms behind effectively.
Yeah.
I feel like you've sort of answered that by saying that once it's out there, it's sort of more available to lots of different people. And
Yeah,
I'm
I
not
think
sure.
I would say like anything else that gets developed, I think there'll be lots of different versions of things. So there'll be free versions, lower cost versions, and versions that only, top end users can use. So I think it's a wide enough domain that there will be that spread, but it's definitely something that we need to think about.
Um, Paddy and James, was there anything you wanted to add to that at all? I feel like
No,
Andrew's.
no, I think overall that I agree 100% with what Andrew said. The only thing that I can maybe add is that one of the things that we are doing in Aberystwyth University to try and make sure that people have more access to kind of training and expertise is we run a summer school that deals with AI, so different departments can come and, learn tools, but it's not a simple or a straightforward process. It is a really difficult, complicated process to understand the problem in the first place and then define it and learn how you'd solve it. So pushing that out to, like, in this scenario, agriculture, I can see could be, really challenging. It's not a straightforward, easy fix.
And I suppose, one thing, just picking up on what Andrew was saying, and one of the questions here as well about the trade-off between, is, um, AI uses like so much, the development stage is using so much energy. What's it does that actually make sense if you're trying to use that AI to reduce emissions? So I wonder whether there's a point where that can be assessed better. Is there going to be a way in the future where, before organizations or research bodies start big AI projects that are going to use a lot of energy, is there going to be a way to assess whether it's worth it in terms of the emissions, particularly if it's trying to reduce emissions? I don't know. Is that something that's being talked about at all? Does
It's
anyone know?
almost cyclical, isn't it? Because you're utilizing your AI to potentially provide insights, and if you plug in the right LCA data within that, maybe there's an opportunity. Yes, there's a high energy demand on the application of AI and the computing costs Andrew mentioned, but if that avoids emissions at the front end, then perhaps there's a kind of a positive trade-off there. Whereas, if you look at perhaps the energy demand of something like a cryptocurrency, not to put them in a different bracket, but maybe not as as useful in terms of application, in terms of reducing emissions on farm. But Andrew, I don't know if you had any comments.
Yeah, so I think you've got to think about the whole system, haven't you? So we often talk about the compute costs of the training because that's where a lot of the heavy lifting of the compute exists. But then if on the user side, actually the end model allows you to analyze things more efficiently, so either quicker or using less power, and as Paddy said, gives you more insight actually into the problem, then that's kind of weighing against that initial investment in compute. So it's a difficult question for sure. But yeah, something we're definitely aware of in the field.
So, just continuing with the ethics side of things. So I asked Chat GPT some questions for this webinar. So I thought that would make sense, and it did some thinking for me. And one of the questions that it raised, was something that Paddy was talking about as well. Is, what are the risks of using AI in terms of displacement of jobs? And I guess there's more of a wider question there around the impact of AI on sort of farming rural cultures, and what that might mean. I mean, Paddy, you mentioned, for example, like nutrition, like animal nutritionists, like could be displaced, for example. I mean, what are
Yeah.
your thoughts? Do you have any more thoughts on what this might mean for that kind of, jobs, cultural identity, that sort of thing.
Yeah, I did mention it to my nutritionist colleague, and she said, "Don't tell everyone because I'll be out of a job." But yeah, no, it's a real world impact, and it's something that's a consequential sort of social impact that we need to evaluate as part of this transition to kind of data driven decision making is the potential displacement on jobs. I guess some of the other social costs you could look at. A lot of farmers don't make decisions based on data. They make decisions based on intergenerational knowledge, on culture, on ties with the land. That is stripped away through data-driven support models. So it's how we integrate some of that local indigenous knowledge into these models is where the gap is, at least from where I see it.
Yeah, thank you. And I think one last question just to wrap up is, I guess, something we've not really touched on, but what's the role of government in all of this to ensure that AI is used in an ethical way, what and sort of effectively as well, and potentially also what's the role of government in ensuring that we can really make the most of this technology for really driving at net zero. Andrew, did you want to comment on that?
Yeah, so I would say, I suppose a plug. So our AI and Biosciences Network, which is funded by BBSSC, is a kind of starting point to try and cover very broadly all the things we've talked about. The training, the consideration of ethics, the making people aware of what's available across quite a broad remit. So there's kind of initiatives like that are getting up and running. But I think everyone, government included, is kind of still trying to figure out how we can use this tool, right? It's literally advanced so fast in the last 5 years that the potential is really exciting. But I think everyone's, trying to work out how this all balances out. So I think it's all in flux, but I think there's some encouraging signs coming along.
Thank you. Does anyone have anything to add before I wrap up at all? No? Good. Okay, good. Well, thank you, everybody. I think that was really interesting. I felt it was a really good introduction. I've definitely learned a lot. Thank you to all of our speakers, Paddy, James, and Andrew. Thank you, everybody, for coming, asking your questions. I hope this was useful. We will, as usual, we'll be putting the webinar on YouTube, and I'll be sending it out probably next week now. So if you want a recap of anything, please take just a couple of minutes also to rate the webinar. I've put a link to it in the chat. Our funding is due to run out at the end of next year, so it will really help us make the case for continuing in some way. If you can kind of rate it, that would be really useful. So our next webinar will be in January with Tim Lang, which will be like quite a big deal. Tim is very, very well known in the sector, in food system space, and he's going to be talking about a report that he has spent 2 years researching and writing, all about effectively the UK's preparedness or not for shocks and stresses. So that's what Tim will be talking about in January. I will be sending out an invite soon. I think it's in the 3rd week of January, 23rd, something like that of January. So I will send that out soon. Also check out our website has a resource hub with all the back catalogue of webinars, plus some briefings based on webinars, digests, and a list of essential reports. So anyway, thank you all, and have a good Christmas.
Thanks, everyone.
Cheers. Thank you.